I'll be using the equation of y equals x squared plus 1 to explain the process of the Euler method and to derive its formula. So after choosing a step size, h, of 0.5 and deriving that my dy dx equals to 2x, I found my approximated y values by using the Euler formula, which is yn plus 1 equals yn plus h, the step size multiplied by the dy dx, which we found was 2x. Moving on to the graph, I selected these 2 points as an example. Firstly, you can see that the difference between my x values of these points is my step size 0.5. Secondly, if I break down the Euler formula, you can see that if I take yn plus 1 minus yn, it will be equals to h times dy dx. So you can see this in my graph. The difference between this point, 19 and 15, is this, h times dy dx. Thirdly, I drew a tangent connecting these 2 points, showing a gradient. The formula of a gradient is rise over run. So if I take this divided by this, the h will cancel out, meaning that my gradient is also the same as my derivative dy dx. We are given the initial values here. So this means that when x equals 0, y equals 1. The step sizes that I've chosen were 0.1 and 0.05 because I wanted to show that with a smaller step size, the more accurate the value of y will be to the exact value of y, which we will derive later on. Thirdly, we have to remember the Euler's formula, which is yn plus 1 equals yn plus the step size times the derivative, which they have provided over here, x squared plus 1 over y. Zooming into the table, I started off with our initial values of x and y, so 0 and 1. And to find dy dx, I simply just use the formula that they've given us. So x squared plus 1 over 1. To find the next value of y, I use the Euler's method. So y0 plus the step size times dy dx. This is how I derive with my y. Instead of copying and pasting the equations, as we go down the column, I simply just selected the previous cell and I dragged it down until I get my value of y when x equals 1. I repeated this for the pink table, and as you can see here, my y values for both tables are different. To derive my exact value of y, I had to use first order ODE. So I started off with this, and I shifted the y to one side, the x to one side, and I integrated everything until I make y the subject over here. After making y the subject, I substituted the initial values of x and y. So I substituted x equals 0 and y equals 1 into this equation to find c. After finding c, I substituted x equals 1 and c equals half into this equation so that I can find my exact value of y. And as you can see, with a smaller step size, my y value is actually a lot closer to the exact value of y compared to the smaller step size. To find the approximation error, the formula is the absolute of the exact value minus the approximated value. So I got 0.00207.